look at the role of network design in supply chain. Also, what are the factors and a framework for making network design decisions. We also make use of some optimization methodologies. So network design decisions can be classified into these four that are listed here. We need to understand what role the facility is going to play and what processes will be used at that facility. So these decisions are very significant because once made, it is going to be very, very difficult to change them, and they can have huge impact on the entire supply chain. So if you look at example of Toyota, before 1997, each plant that they had was capable of serving only the local market. But during late 1990s, when Asian economy had a big recession, so most of the plants that Toyota had in that region had to be kept idle because of falling demand. So with that experience, Toyota has now added more flexibility to their plants, where the plants are able to serve not only the local markets but other markets as well. Facility location has a major impact on supply chain performance, and once a facility is located somewhere, it is very difficult to move them or shut them down because that will be very, very expensive. Capacity allocation decisions involve answering questions like how much capacity we should have at each facility. Capacity decisions are probably slightly more flexible than facility location decisions because capacity at times can be altered. However, once a decision is made, then that stays for a very long time, and if there is excess capacity, that will lead to low utilization, which will increase overall cost. But if the capacity allocated is very little compared to what is needed, so that will cause poor responsiveness. So what markets these facilities should serve and which supply source will feed these facilities. So note that these network designs must be revisited from time to time because of changes in markets, or there could be mergers, or because of cost regions. Netflix, for example, had 58 distribution centers around 2010. The idea was to lower the transportation cost for shipping DVDs and improve responsiveness. But when video streaming started gaining popularity and DVD rentals reduced, so Netflix closed about 20 distribution centers by the end of 2013. Similarly, Amazon, because of increase in demand, doubled their distribution centers from 20 to 40. So they had 20 in 2009, which rose to 40 by 2013. So there are so many factors that have impact on network design decisions. Let's look at some of them in addition to what we have seen in earlier chapters. So there are strategic factors. Competitive strategy has big impact on network design decisions. For example, a business that is competing on cost, they will try to locate their manufacturing at places where the labor cost is very low. And that's the reason if you look at major IT companies like Apple, Amazon or Google, so they have located their manufacturing in China, and companies such as Foxconn does majority of manufacturing there. That helps them to reduce cost. Another example you can say is convenience stores. They compete on responsiveness. If you look at any major city, there may be many convenience stores that help a customer to locate them very easily. And to travel to each convenience store, a customer may not have to travel very far. On the other hand, if you look at discount stores like BJ's or Sam's Club or Costco, so usually they have a very large store. Customers have to travel sometimes several miles to shop at these locations. Another important factor is technological factors. The production technologies that are available at a given time, so they have a very big impact on decisions involving network design. So one example is manufacturers of computer chips. So manufacturing computer chips requires a huge investment in a manufacturing facility, but the output is relatively inexpensive to transport. So on the other hand, if you compare a company like Coca-Cola, they may have several bottling plants because bottling plants do not have very high fixed cost. Macroeconomic factors. So nowadays, every business is impacted by globalization, and businesses compete with companies to gain market share globally. And many countries require these companies to have local plants. Obviously, these companies negotiate with these governments to have some incentives to open a plant in their countries. So recently, for example, Apple has been negotiating with the Indian government to open an iPhone manufacturing plant in India. And they are looking to gain some incentives so that it is win-win for both. So the company gets some incentive and then it provides a lot of jobs for local people. Another macroeconomic factor that businesses have to keep in mind that has impact on network design decisions is exchange rate and demand risk. So depending on the economy and many other factors, currencies usually fluctuate, and that creates a lot of challenge for businesses which are competing globally. So for example, if a company is in US and dollar becomes strong, then exports will be hurt. Freight and fuel costs also play a very important role. So we have seen in 2008 and 2009, oil prices were very high, and in 2016 and 17 it has come down a lot. So obviously it has a big impact on network design decisions because they directly impact transportation cost. Political stability of a country is definitely important when deciding where to locate a facility. Infrastructure factors are also very critical. For example, if a facility is located in a country where infrastructure is not good, so in those places transportation costs may be very high. Availability of good roads or railways or closeness to airports, all those play an important role when deciding about network design. Any business competing in a global competitive environment has to take into account competitive factors. So positive externalities between firms occur when firms find it beneficial to locate near each other. Retail stores, for example, try to locate near each other because that will lead to increase in demand and everyone benefits from that. So many retailers locate together in a mall, which makes it very convenient for the customers because they go at one place and they are able to shop at different retailers. Another example is of a Japanese automaker, Suzuki, which had a partnership with the Indian automaker called Maruti. So when setting up a manufacturing plant, Suzuki had to develop a network of suppliers. And once a good supplier base was developed in India, it made easier for many other automakers to come in and benefit from that. When there are no positive externalities, then companies try to locate in such a way that they can get the maximum possible market share. So when businesses compete on distance from the customer, like how much customer has to travel. Now suppose we have a total demand of 1 and there is a company which locates at location A and other company at 1 minus B. So company which is located at A attracts the customer which are located from 0 to A and splits half of customers between A and 1 minus B. Suppose demand at A is given by D1. So D1 will be equal to A plus 1 minus B. So from there we subtract A and half of that. Similarly for second company, so it will be B plus again 1 minus B minus A over 2. In fact, if you rearrange, we get 1 plus B minus A over 2. So basically, both companies will maximize their market share if they move closer to each other. So ideally, if this is 0 and this is 1, so if both companies, they locate at midpoint, that will be the ideal situation. So this is based on companies that compete on distance. If companies are competing on price, and customers incur the transportation cost, it may be good for those companies to be as far from each other as possible. So when they locate far from each other, that will minimize price competition and help companies to split the market and maximize profits. Customer response time and local presence is another key factor that has impact on network design decisions. Companies like BJ's or Sam's Club, they target customers who are less time sensitive. But if customers like shorter response times, obviously they will like to go to some kind of convenience store. So there are many situations where facility must be located closer to the customers, and one example is coffee shop. So obviously a customer will not like to travel several miles to have coffee. So logistics and facility cost. So Amazon have fewer distribution centers if you compare with the number of stores that Barnes and Noble has. So Barnes and Nobles has hundreds of stores but has lower transportation cost. So let's look at the framework for network design decisions. You can see in this picture it is divided into 4 phases. In the first phase, we define a supply chain strategy which takes into account what is the competitive strategy of the company. For example, whether they want to compete on cost or responsiveness. It also looks at internal constraints that the business has in terms of capital, growth strategy, whether existing facilities will be used or new ones will be acquired and so on. It also identifies global competition. So a broad supply chain strategy is identified in phase 1. And then we move to phase 2, where regional facility configuration is defined, and the objective of this phase is to identify regions where the facilities will be located. So at this stage, it is important to take into account what production technologies will be used, and also looking at how much it will cost, what flexibility it should have, scale and scope, and also what support will be required. At this stage, again, we look at competitive environment, like what players exist in the market, what supply chains they have. At this phase, managers also look at tariffs and tax incentives, which could be possible depending on where they would like to locate their facilities. They also develop a forecast for the demand. So what is the size of the demand? Is there a scope of growth? Whether or not it is homogeneous? And what are various local specifications? This phase also takes into account the political situation of the location, exchange rates, and demand risk that may exist. Another input to this phase is aggregate factor and logistics cost. So managers must look into the possibility of making use of economies of scale that can help in reducing cost. Once decision makers move to phase 3, the objective is to identify desirable sites where the facilities can be located. Obviously, production methods is an important input. So what skills will be needed at these production sites? What is the response time? And managers also must take into account what is the available infrastructure. There could be hard infrastructure requirement in terms of availability of suppliers and whether or not transportation services are available, communication services, utilities, warehousing facilities, etc. And soft infrastructure requirements could include whether or not skilled workforce is available. And the last phase involves making location choices. So out of potential desirable sites, precise location and capacity decision is made here. While making this decision, all the factors need to be taken into account. So cost factors could involve labor, material. It could be costs that are like site specific. So logistic cost involves transportation, inventory, and coordination activities. So there are several models that are available that help in facility location and capacity allocation. Objective is to maximize the overall profitability of the supply chain network, at the same time providing customers with appropriate responsiveness. Cost and responsiveness obviously need to be balanced. So there are many trade-offs that need to be made during any network design. So for example, if a business decides to make several facilities, so that will obviously reduce transportation cost and provide good responsiveness, but it will also increase facility and inventory cost. So managers who make these decisions, they use network design models in two situations. One is to decide on locations and their capacities, and other one is to assign current demand to facilities and identify transportation lanes. We may have several facilities available and there may be demand from various locations. So which facility should cater to demand at which location? So those decisions need to be made. So let's look at some mathematical models that can be used in various phases. In phase 2, we are defining the regional facility configuration. In this phase, network optimization models could be quite useful. One example of this model is given here. It's called Capacitated plant location model. So there are several inputs that are needed for this model. So these are the inputs and decision variables are given here. So yi is 1 if plant I is open and 0 otherwise. Xij is quantity shipped from plant I to market J. So this problem can be formulated as a mixed integer program. If you look at this objective function here, Fi is annual fixed cost of keeping plant I open, and y is whether or not the plant is open. So in this model, we have this part which is capturing fixed cost, and then we have second part which captures variable cost. So fixed cost is something which is not impacted by the quantity. Whether we have 1 or 100, it doesn't matter. But the variable cost is something which is impacted by quantity. So as the quantity increases, variable cost will obviously go up. So if you look at the constraints here, this first constraint means all the demand should be satisfied. Second constraint basically says supply can't be more than capacity. And this third constraint basically says that plant is either open or closed. Let's look at one example. So data that we have here includes 5 manufacturing locations: North America, South America, Europe, Asia, and Africa. And items that are produced here will be sold in these markets. The data that you see is in thousands of dollars, and this is for production and transportation cost per 1 million units that is produced. So for example, it will cost $81,000 to produce items in North America and sell in North America. Similarly, it will cost $92,000 to produce 1 million units in North America and sell in South America. So obviously when the distances are large, this cost is going to be large too. So for example, it will cost $142,000 to produce in Africa and sell in North America. We also have data on demand in each of the regions. So note that all the numbers are in millions and all the dollars are in thousands. So this 12 means in North America demand is 12 million, in South America it is 8 million, and so on. Another data that we have is fixed cost. So to manufacture in North America, fixed cost is $6 million, whereas to manufacture in South America, fixed cost is $4.5 million. And this fixed cost is for situations when we have low capacity. Here we are considering situations where capacity will be 10 million units. But if we want to go for higher capacity, which is a double of the low capacity, so manufacturing in North America will cost $9 million with a capacity of 20 million units. This fixed cost is 1.5 times higher than fixed cost for low capacity. So you'll see that in this column we have multiplied the numbers by 1.5 to get these new numbers. Once we have this data as input, we want to make decisions about which region should be served from which manufacturing location. So essentially, we look at this total demand in each region, and then we try to find out which manufacturing location will fulfill demand in that region. We also have decision variables in terms of whether we should go for a small plant or large plant. So if it is 1, it will mean that we go for a small plant here, but if it is 1 here, it means that we should go for a larger plant. In these cells, we have formulae to find excess capacity, and basically this is to have a constraint where a manufacturing plant cannot produce more than the capacity. So excess capacity has to be 0 or greater. And if you look at the formula here, so we have this cell which is G14 times H4, number of plant in that manufacturing area times the capacity. So for example, if we have 1 here, that means we'll be able to produce 10 million units. But if we have 1 here, then we are able to produce 20 million units. Minus sum of B14 to F14. So it is sum of whatever numbers appear here. So this will make sure that we do not get any negative value here. If you look at the objective function, so we have B14 to F18, so this blue rectangle, and B4 to F8, which is this red rectangle. What we do is, so 81 times whatever number we get here, plus 92 times whatever number we get here, and so on. So that is the sum product. The next part is G14 to G18. So wherever the small plant is, times G4 to G8. So this will give us fixed cost whenever we have a small plant, and this last part gives us fixed cost whenever we have large plant. To use solver, we click on data, and usually solver will be somewhere here. If you don't see it, that means we need to add it. For doing that, you can go to tools and Excel add-ins, and then select both of these and say OK. So next time when you click on data, you'll see that there's a data analysis option, and also there is a solver option. Let's click on solver. So we have this window that comes up. It already has information. To set an objective, we choose this cell, point towards the cell that we want to optimize. So we want to minimize the total cost, so we choose minimum. By changing variable cells, so you can see that we have already selected these cells here, and that's what you see here. So we have selected from B14 up to H18. So these are the decision variables. Next we have constraints. So first constraint is B14 to H18, which is all the decision variables. So they have to be greater than or equal to 0. Second constraint is B22 to B26. This has to be greater than or equal to 0. So basically it means that a manufacturing plant cannot produce more than the capacity. Third constraint is B28 to F28. So all these demand numbers become 0, which means that the solution should make sure that all the demand is met. And then finally, we have another constraint, G14 to H18. They are binary. 0 will mean no plant and 1 will mean there is a plant. If I delete this, and if you want to add it back, then we select all the cells that we are interested in, and we want to say this should be greater than or equal to 0. And once we say OK, that constraint gets added. So this is how we can add any number of constraints. And for solving, we have 3 different methods. So right now we are going to use simplex linear programming, LP. And once you hit solve, it will find the solution. So if we say OK, it will keep all the solutions. So you can see the decision variables have taken some values now. And the solution says that we should produce 12 million units in South America to fulfill demand in North America. Also, we should make another 8 million in South America to fulfill demand for South America. If you look at the overall solution, it says that we should go for 3 large plants, one in South America, one in Asia, and one in Africa. So based on the data, these 3 plants will minimize the total cost. So the total cost comes to $23,751,000. And you can see that all the demand are met. The only thing you may see is in Africa we have some excess capacity of 3 million units. The manufacturing plant in Africa is going to be underutilized. Using this model, we can also try some what if situations. For example, what if a plant must be built in Europe? So we want this number to be 1. So we can add a constraint and say that I16 must be greater than or equal to 1. So let's try that. So we add a constraint and we say I16 is greater than equal to 1. And then we hit solve. So we get a solution which is slightly different from the previous one. So now we have plants in Europe, Asia, and Africa. And we have plant in Europe because we put a constraint that we must have a plant in Europe. Because of that extra constraint, the total cost has gone up by about $3 million. What if plants must be built in every market? Let's go to solver. So we'll delete this one and add a new one and select these 5 cells. And we want this to be greater than or equal to 1. Click OK. So this constraint is added now, which will make sure that there's a plant either small or large in every region. So we click solve and wait for a few seconds and we have the solution. You can see that the overall cost goes further up. Now it is 31.5 million and above. But now we have fulfilled the requirement of 1 plant in every region. So that comes at an extra cost. The solution says that we should have small plants in North America, South America, and Europe, as well as Africa. And we must have a large plant in Asia based on data that we have. So in the framework, we saw that in phase 3, basically managers make decisions about potential locations, and gravity location models can be very useful when identifying suitable geographic locations. So model inputs involves XY coordinates for the location. So that location may be either the market where the demand is, or it could be a supply source or manufacturing plant. Fn denotes the cost of shipping 1 unit for 1 mile between facility and either market or supply source, and Dn represents quantity to be shipped between facility and the market or supply source. So if we consider the new facility to be located at XY, then we can find distance of this new location XY with the help of coordinates of other location XN or YN. So this is the standard formula that we use, and the total transportation cost is given by multiplication of this distance, the quantity, and the cost. Let's look at one example. So here we want to find a new location for a plant, and we are trying to arrive at the coordinates that will minimize various costs. We have 3 sources from where parts will move to this new location, and then there are 5 markets that we are interested in. It will cost 90 cents per ton to move parts from Buffalo to this new location by a mile. And the total items to be moved at this source is 500 ton. And these are the coordinates. Using these coordinates and the coordinates of new location, we can find the distance using the distance formula. So that formula is entered here. And then if you look at the cost, so this is a multiplication of column C, column D, and column G. That will give the total cost. We also have this picture here where this pink dot represents the new location. So initially location has been set at 0, but once we optimize, we'll find accurate location that will minimize the total cost. So we go to solver. So data and solver. So this is the objective function that we have, and we want to minimize this. So this is minimum by changing the variable cells. So by changing this X and Y values from 0 to anything different. And the method that we are going to use is grg nonlinear. So once I hit solve, so it comes out with the new locations. We can say OK. You can see that the coordinates for this new plant, which is represented by pink dot, is somewhere here. If we change tonnage from St. Louis, which is here 700 tons, to 1700 tons. So what will happen is, because now we are moving more material from this location to the new plant, this pink dot should go closer to St. Louis. And St. Louis is located at 225, 825, which is this dot here. You can also note that when we have changed this from 700 to 1700, the cost numbers also changes. So we have this new location, which is closer to St. Louis. And what if it changes to 2700, so even more? Then this pink dot is obviously going to go even closer, because now this location has a very high weightage. You can see that the new plant should almost be located at the same location as the source that supplies the parts. So in phase 4, a manager decides on location and capacity allocation for each facility. So here we can use several examples, starting with the allocating demand to production facilities. So we have a set of model inputs, and then we have decision variable Xij, which is quantity shipped from facility or factory I to market J. So the idea is to minimize the cost. So this is a total cost of shipping these items, where Cij you can see is the cost of producing and shipping one unit from factory I to market J. This constraint basically makes sure that all demand is satisfied. And second constraint basically makes sure that a factory's production is less than or equal to capacity. So we cannot produce more than the capacity of that facility. So here we have these 5 supply cities, and there are 6 demand cities. We have production and transportation cost per 1000 units. Note that this is in thousands of dollars. For each supply city, we have fixed cost, which is in thousands of dollars. So at Baltimore, the cost is going to be $7,650,000 with a capacity of 18. So this is also in thousands, so 18,000 units. We also have demand from all the demand cities. So initially we look at a company called High Optic. This company supplies from these 2 locations, and the demand cities are Denver, Omaha, and Portland. So we want to figure out where should we locate the plant out of these 2, and how much demand will be fulfilled from each location. Among the constraints, what we have is the plants obviously cannot produce more than the capacity, and other constraint is that all demand has to be met. Our objective function is basically some product of this blue rectangle times the cost of moving items from the supply location to demand location. That will give us this total. And then the second sum product is basically multiplication of fixed cost depending on where the plant is located. So we want to minimize this cost function. So we go to data and solver. So this is the objective function. So this is location, and we want to minimize this. And these are the decision variables that we have to arrive at. And we have the constraints like B23 should be positive. It cannot be negative. Similarly, B24 should be positive. Similarly, these numbers in the blue rectangle should be all greater than or equal to 0. demand at these three locations, Denver, Omaha and Portland. That should be met. So this should become 0. So we have everything. So let's click on solve. So it says the linearity conditions required by LP solver are not satisfied. Let's go back again and change this from simplex LP to GRG nonlinear and hit solve. Solver found a solution. All constraints and optimality conditions are satisfied. So we can say OK. So you can see that one plant each is needed at both of these locations. And from the first location, demand is fulfilled for Denver and Omaha. And from Salt Lake, demand for Portland is fulfilled. So total cost for this comes to $21.365 million. So note that in this plants column, I have created a if function, and if the sum is more than 0, then only any one of these cells will get a value of 1. Otherwise, it will be 0. So 1 will mean there is a plant and 0 means no plant. If you look at the second company, which is Telecom 1, so we have same data and we have these blue cells which are relevant for this analysis. So we do the same thing. We go to solver and hit solve. So again, I think we need to go nonlinear because linearity conditions required by LP solver are not satisfied. So let's do that. GRG nonlinear and hit solve. So we get some solution. We can say OK. So you can see that this solution will cost about $26.636 million. And you can also see all the demand at the three locations, Atlanta, Boston and Chicago, are met. So the solution says that we should use plants at Baltimore and Memphis, but not the one at Wichita. That's why Wichita will have excess capacity of 31,000 units because it is unused. In the previous example, we had two separate companies, and now we consider that they are merged into one. We can solve this using location specific costs, and we have seen a model where we have fixed cost and the variable cost that we want to minimize. Here we assume that these two companies, High Optic and Telecom 1, they get merged into one, Telecom Optic. Now we can optimize the entire matrix at once, and let's see what we get. So we have similar constraints and we hit solve. So we have a solution. So once you say OK, you can see that the total cost is about $47.401 million. So remember earlier we had 21.3 plus 26.6, about $48 million. That has come down to $47.401 million. And this solution says that we should make use of plants in Baltimore, Cheyenne and Memphis. So you can see all the demand is fulfilled, and there will be excess capacity of about 8,000 units in Baltimore. So there are some situations where we use capacitated model with single sourcing. There are many companies that want to design supply chain networks in such a way that a market is supplied from only one factory, so which we call single source. This design basically helps in reducing complexity and improves coordination, so it has a lot of benefits. So these two constraints basically ensure single source, which means each market is supplied by exactly one factory. So once we find the solution, we find that it adds about $2.3 million to the overall cost. So here we want to have a model where each market is supplied from a single source. Basically, if you look at these decision variable cells, each column should have just one number. And let's look at the solver B14 to G18. So all these should be binary. So it will be either 0 or 1. And then B31 to B35. So we are saying that it should be greater than or equal to 0. And then we have these cells from B38 to G38 is equal to 1. which means that all of these should be equal to 1. So if you look at this cell here, for example, Portland, so it is a total of this column. So when it is 1, it means that Portland should be served by one and only one source or supply. So let's solve this. All constraints and optimality conditions are satisfied, so we say OK. So you can see it will cost about $49.717 million. And if you look at this cell here, so you can see Atlanta will be served by Memphis, Boston 2 from Memphis, Chicago will be served by Wichita, Denver, Salt Lake, Omaha, Wichita, and Portland from Salt Lake. So these two will be unused. And then here we have resulting production allocation. We multiply this cell by this number here, which means 10,000 units should be produced at Memphis to satisfy demand at Atlanta. Another 8,000 units should be produced here to satisfy demand at Boston. Similarly, you can see other numbers. A more general, although very complex model will be where we have the entire supply chain network, including suppliers, manufacturing plants, warehouses, and finally the market. In this supply chain, supplies are sent from suppliers to manufacturing plants, and then we have items shipped from plants to warehouses and finally to the customers. So there are several model inputs that are to be considered. So all of them are listed here. And the goal is to identify plant and warehouse locations and quantities shipped that minimizes the total fixed and variable cost. So if you look at the model in terms of model inputs and decision variables, so this is listed here. First component, which is a fixed cost related to the plant, and then we have fixed cost related to the warehouse, and then we have variable costs, and this variable cost involves cost associated with supplying from supplier to plants, and then we have variable cost, so this is from plants to warehouse, and then this component is variable cost associated with warehouse to customers. Similarly, we have constraints. This one says total which is supplied from the supplier cannot exceed supplier's capacity. Second one says that the amount that is shipped out of a factory cannot be more than the quantity of raw material received. And then we have amount that is produced in the factory cannot be more than the capacity of that factory. This one says the amount shipped out of warehouse cannot be more than the quantity received from factory. Similarly, this one is amount which is shipped from the warehouse cannot exceed the capacity that warehouse has. So if a warehouse can store, let's say hypothetically, only 100 items, so that warehouse obviously cannot ship 200 items. This one says that the amount that is shipped to the customer basically should cover the demand. So if there is a demand for 10 items, all that demand should be met. And this last one says that the factory or the plant or the warehouse is either open or closed. We can always add more and more constraints and make the model very complex, but it also becomes very difficult to solve such models. So accounting for taxes, tariffs, and customer requirements. A supply chain network should maximize profits. That's the main objective, but that should be after tariffs and taxes. So that need to be taken care of while meeting customer service requirements. So we can actually modify earlier model that we have seen. We basically minimize the costs, fixed cost and variable cost. But if you take into account revenues, then we can develop a model that maximizes the total profits, taking into account tariffs and taxes. So when making a network design decisions in practice, we need to be careful about few things. One is, do not underestimate the lifespan of facilities. Investments in facilities is a huge investment, and generally once it is made, it is difficult or very expensive to change. So, while making the decisions, it is important to understand long term consequences of facility decisions. So, it has also been found in most supply chains, production facilities are more difficult to change compared to storage facilities. So, managers who are making decisions to have production facilities should keep in mind that those production facilities are going to be there for a very long time. But storage facilities or warehouses, especially which are not owned by the company, so those changes are relatively easier. Do not gloss over the cultural implications. Decisions that involve facility location and role for those facilities, so that also must take into account cultural aspects. Decision makers should look into who are the people who are going to work. Do not ignore quality of life issues. Facilities where people are going to work, there are so many other things involved. So people may live with their families, they may be looking at what kind of schools that location has for their kids. So quality of life issues cannot be ignored if business want to attract workforce that find working at that facility rewarding. Focus on tariffs and tax incentives when locating facilities. These could be very big because creating these facilities like a manufacturing facility or warehouses, these also create a lot of job opportunities, and businesses often communicate with the governments and try to get tariff and tax incentives to locate their facilities in those areas.